Hey everyone, welcome. Today we're going to roll up our sleeves and tackle one of the coolest properties in all of mathematics. We're going to walk through, step by step, and prove this beautiful recursive property of the gamma function. Let's get into it. Okay, so first things first, what even is the gamma function? Well, here it is. We write it as gamma of alpha. And for any positive real number alpha, you find its value by solving this improper integral. It's the integral from 0 to infinity of t raised to the power of alpha minus 1, all times e to the minus t. And this is our goal for today. This incredibly simple and powerful relationship is what we're here to prove. It basically says that the gamma of alpha plus 1 is just alpha times the gamma of alpha. Now, the key to unlocking this whole thing is a tool that I'm pretty sure you'll remember from your first calculus course. And that tool is integration by parts. But before we just jump in and start using it, let's do a real quick refresher on where this thing even comes from. Because it's not some kind of magic formula, right? It actually comes from something even more basic. It all starts right here with the good old product rule for derivatives. You remember this, right? The derivative of two functions multiplied together, u and v, is just the derivative of the first times the second, plus the first times the derivative of the second. Simple enough. So to build our more powerful tool, we literally just integrate both sides of the product rule. On the left side, the integral of the derivative of uv just simplifies back to uv. And then all we have to do is a little bit of algebraic shuffling to isolate one of those integrals, and we get our final formula. And voila. That leaves us with this, the integration by parts formula. The integral of u dv is equal to u times v minus the integral of v du. This is the key that's going to let us crack the code of the gamma function. All right, our tool is sharpened, and it is time for the main event. Let's see exactly how we can use this to transform the integral for gamma of alpha plus 1 into what we want, alpha times the integral for gamma of alpha. So, naturally, we start with the left side of the equation we want to prove. Using that definition we just talked about, gamma of alpha plus 1 is the integral from 0 to infinity of t to the power of alpha times e to the minus t. Okay, now here comes the most important part of any integration by parts problem. We have to break this integral into two pieces, a u and a dv. I mean, the entire success of this proof really hinges on making a smart choice right here. So what's it going to be? So here's our strategy. We're going to set u equal to t to the alpha. Now, why do that? Well, think about it. When we take its derivative to find du, the power on t goes down by 1, which gets us one step closer to what gamma of alpha looks like. And that means dv has to be e to the minus t dt, which is super easy to integrate to find v. Perfect. We've got our four puzzle pieces, u, dv, du, and v. Now it's just a matter of plugging them straight into that integration by parts formula we just reviewed. And this is what we get once we plug everything in. So you see, our original integral is now broken into two distinct parts. We've got this first part, the uv term, that we need to evaluate at the boundaries. And then we have this new integral, the integral of v du. You know what? Let's zoom in and tackle that new integral on the right-hand side first. It might look a little messy, but notice we've got a minus sign out front, another minus sign on the inside, and that constant alpha that we can just pull out. And when we clean that up, things get nice really fast. The two negative signs, of course, cancel out and become a positive, and we can pull that constant alpha completely outside the integral since it has nothing to do with t. And would you look at what we're left with? The integral that remains is t to the alpha minus 1 times e to the minus t. Wait a second. That is the exact definition of gamma of alpha. This is huge. That whole second half of our expression just simplified down to alpha times gamma of alpha. That's the right side of the thing we're trying to prove. We are so close. We've already got half of our answer. Now all we need to do is figure out what's going on with that first term, that uv part, when we evaluate it at our limits, infinity and 0. Okay, so let's look at the boundaries. First, as t shoots off to infinity, you've kind of got a battle going on. The t to the alpha part wants to get huge, but the e to the minus t part wants to shrink to 0, and it wants to do it really fast. Well, let me tell you, exponential decay always wins that fight. It crushes the polynomial growth, so the whole thing goes to 0. And at the other end, as t goes to 0, well, that t to the alpha factor just becomes 0, making the whole thing 0 again.
So the punchline here is that this entire first piece of our puzzle, what we get at the upper bound minus what we get at the lower bound, is just 0 minus 0. The whole term, it just vanishes.
We did it. We've solved both parts. And now for the really satisfying part. Let's put all these pieces back together and watch the final proof just fall into place. So let's just do a quick recap. We started with gamma of alpha plus 1. We used integration by parts to split it into two terms. We just proved that the first boundary term goes to 0. Poof. And we saw that the second integral simplifies beautifully into positive alpha times gamma of alpha. And there it is. Our starting point equals 0 plus alpha times gamma of alpha, which is just alpha times gamma of alpha. We've done it. We have successfully proven this fundamental property of the gamma function. Isn't that just an elegant result from such a classic technique?
It's really a perfect example of how a simple, repeating rule can build something incredibly complex and powerful. And this is a pattern you see absolutely everywhere, right? From fractals in nature to how algorithms work. So it makes you wonder, what are some other complex problems out there that are secretly solved by simple, recursive rules? Thanks for exploring this one with me.